Hi, welcome to the ComSci 137 lecture. Sunny here. Now, we will discuss part 2 of the digital transmission module. Let's start. Digital signal is superior to analog signal because it is more robust to noise and can easily be recovered, corrected, and amplified. The tendency today is to change analog signal to digital data. It's called digitization. There are two common techniques, the pulse code modulation or PCM and delta modulation. PCM consists of three steps to digitize an analog signal: sampling, quantization, and binary encoding. Before we sample, we have to filter the signal to limit the maximum frequency of the signals as it affects the sampling rate. Filtering should ensure that we do not distort the signal or remove high-frequency components that affect the signal shape. The first step in PCM is sampling. Analog signal is sampled within a certain time period, called sampling period or sampling interval. The inverse of sampling period is called sampling rate or sampling frequency. This process is referred as pulse amplitude modulation or PAM, and the outcome is a signal with analog values. The sampling rate must be at least twice the highest frequency in the original signal. There are three sampling methods: ideal, natural, and flat top. In ideal sampling, pulses from the analog signal are sampled. This is an ideal method, but it cannot be easily be implemented. Natural sampling, a high-speed switch is turned on for only the small period of time when the sampling occurs. The result is a sequence of samples that retains the shape of the analog signal. The most common sampling method, called the sample and hold, creates flat-top samples by using a circuit. One important consideration is the sampling rate or frequency. What are the restrictions? This was answered by Nyquist. According to the Nyquist theorem, to reproduce the original analog signal, one necessary condition is that the sampling rate be at least twice the highest frequency in the original signal. In this figure, the sampling rate created a good approximation of the original sine wave. Here, where there is oversampling, it also produces the same approximation, but there is redundant and unnecessary. Here, the sampling rate is below the Nyquist rate, so it did not produce a signal that looks like the original sine wave. The next step in PCM is quantization. The result of sampling is a series of pulses with amplitude values between the maximum and minimum amplitudes of the signal. The set of amplitudes can be infinite with non-integral values between the two limits. These values cannot be used in the encoding process. It needs to be mapped onto a finite set of known values. First, we divide the range into L zones, each of height delta. Next, assign the quantized values of 0 to L-1 to the midpoint of each zone. We then approximate the value of the sample amplitude to the quantized values. As a simple example, assume that we have a sample signal and the sample amplitudes are between -20 and +20 volts. We decide to have 8 levels. This means that the delta is 5. The figure, we have shown only 9 samples using ideal sampling. The value at the top of each sample in the graph shows the actual amplitude. In the chart, the first row is the normalized value for each sample. We got this value by dividing the actual amplitude by the delta. The quantization process selects the quantization value from the middle of each zone. This means that the normalized quantized value, 1 in the second row, are different from the normalized amplitudes. The difference is called the normalized error, the third row. The fourth row is the quantization code for each sample based on the quantization levels at the left of the graph. The encoded words, the fifth row, are the final products of the conversion. The last step in PCM is encoding. We saw this in the previous slide. Each zone is assigned a binary code. The number of bits required to encode the zones is obtained as follows. Given in the previous example, the number of bits required is 3. Bit rate of a PCM signal can be calculated by multiplying the number of bits per sample and the sampling rate. Bandwidth required to transmit this signal depends on the type of line encoding used. A digitized signal will always need more bandwidth than the original analog signal. Question: what is the bit rate needed to digitize human voice assuming 8 bits per sample? Human voice contains frequency between 0 to 4000 Hz. Using the formula, we need 64 kilobits per second. To recover an analog signal from a digitized signal, we use a circuit that holds the amplitude value of a pulse till the next pulse arrives. Pass this signal through a low-pass filter with a cutoff frequency that is equal to the highest frequency in the pre-sampled signal. The higher the value of L, the less distorted a signal is recovered. Delta modulation finds the change from the previous sample. The modulator is used at the center site to create a stream of bits from an analog signal. The process records the small positive or negative changes, called delta. If the delta is positive, the process records a 1. If it is negative, the process records a 0. However, the process needs a base against which the analog signal is compared. The modulator builds a second signal that resembles a staircase. Finding the change is then reduced to comparing the input signal with the gradually made staircase signal. The modulator at each sampling interval compares the value of the analog signal with the last value of the staircase signal. If the amplitude of the analog signal is larger, the next bit in the digital data is 1. Otherwise, it is 0. The output of the comparator, however, also makes the staircase itself. If the next bit is 1, the staircase maker moves the last point of the staircase signal delta up. If the next bit is 0, it moves its delta down. Note that we need a delay unit to hold the staircase function for a period between two comparisons. At the demodulator takes the digital data and using the staircase maker and the delay unit, creates the analog signal. The created analog signal, however, needs to pass through a low-pass filter for smoothing. Of primary concern when we are considering the transmission of data from one device to another is the wiring. And of primary concern when we are considering the wiring is the data stream. The transmission of binary data across a link can be accomplished in either parallel or serial mode. In parallel mode, multiple bits are sent with each clock tick. In serial mode, one bit is sent with each clock tick. Binary data, consisting of ones and zeros, may be organized into groups of n bits each. Computers produce and consume data in groups of bits, much as we conceive of and use spoken language in the forms of words rather than letters. By grouping, we can send data n bits at a time instead of 1. This is called parallel transmission. The mechanism for parallel transmission is simple. Use n wires to send n bits at a one time. That way, each bit has its own wire, and all n bits of one group can be transmitted with each clock tick from one device to another. The advantage of parallel transmission is speed. All else being equal, parallel transmission can increase the transfer speed by a factor of n over serial transmission. But there is a significant disadvantage: cost. Parallel transmission requires n communication lines just to transmit the data stream. Because this is expensive, parallel transmission is usually limited to short distances. In serial transmission, one bit follows another, so we need only one communication channel rather than n to transmit data between two communicating devices. The advantage of serial over parallel transmission is that with only one communication channel, serial transmission reduces the cost of transmission over parallel by roughly a factor of n. Since communication within devices is parallel, conversion devices are required at the interface between the sender and the line, and between the line and the receiver. Serial transmission occurs in one of three ways: asynchronous, synchronous, and isochronous. Asynchronous transmission is so named because the timing of a signal is unimportant. Instead, information is received and translated by agreed upon patterns. As long as those patterns are followed, the receiving device can retrieve the information without regard to the rhythm in which it is sent. Patterns are based on grouping the bit stream into bytes. Each group, usually 8 bits, is sent along the link as a unit. The sending system handles each group independently, relaying it to the link whenever ready without regard to a timer. There is no synchronization at the byte level, but it is present in the bit level. Bits can be transferred at random intervals, and the data rate of the stream is not required to be constant. In synchronous transmission, the bit stream is combined into longer frames, which may contain multiple bytes. Each byte, however, is introduced onto the transmission link without a gap between it and the next one. It is left to the receiver to separate the bit stream into bytes for decoding purposes. In other words, data are transmitted as an unbroken string of ones and zeros, and the receiver separates the string into bytes or characters it needs to reconstruct the information. Without gaps and the start and stop bits, there is no built-in mechanism to help the receiving device adjust its bit synchronization midstream. Timing becomes very important, therefore, because the accuracy of the received information is completely dependent on the ability of the receiving device to keep an accurate count of the bits as they come in. Isochronous transmission combines the features of an asynchronous and synchronous data transfer system. Isochronous transmission guarantees that the data arrive at a fixed rate. Each transmission begins with a start packet, and it is mostly used in multimedia data. This ends Module 7. Thank you.